Hello everyone, welcome to the week 9 of Coherence and Quantum Entanglement course. Today is 23rd of March, where we are going to discuss again about this course, Coherence and Quantum Entanglement, floated by NPTEL through SWAM portal. And I am your TA Nilakshi Shenapati from IIT Kanpur, and this course is instructed by Professor Anand Kumar Jha from IIT Kanpur. And these are the problem solving and doubt clearing sessions which happens every Saturday from 5 p.m. to 7 p.m. And the lectures are already uploaded there in the NPTEL Coherence and Quantum Entanglement course in the SWAM portal. These all the things are known to you, but still this is a formal starting of the course like every other Saturdays. So I mention each and every time for again and again. So this is just to welcome you back to this course. So we have only 3 weeks left. Today is the 9th week. Another 3 week we will continue this journey. For week 9 we have some plan. We now our main focus is on the problem solving part, because theory is conducted and lectures are given in a very beautiful and organized manner in the in your lectures. While I will first give you some glimpses of understanding and understanding, and as well as to recapitulate the things that what have already taught to you. And once that is done, our main focus is always to solve the problem such that you face no problem during the during solving uh, the quizzes or assignments, and as well as your NSEM or final examination. So keeping these things in mind, we organize and we conduct these problem solving and doubt clearing classes, where you can join and directly ask the questions to us. And whatever I am teaching or I am discussing here with you, all the things are all the things are uploaded there in the Google Drive folder. that Google Drive folder is shared with you already through the through by NPTEL through SWAM portal. But again, I am sharing the Google Drive link where you can get all of these class notes, slides, discussions, extra materials, whatever I want to I find. I used to supply those to you through this Drive folder link. And all the lecture notes, all the class discussion session notes, of course you will get there. And if somehow you miss the session, then you can always visit the YouTube channel link, YouTube channel, where you will get the um, this the recorded session of this problem solving and doubt clearing sessions. So those or either you can search my name, that is my channel only, and you can give I mean, you can even turn on the notifications to get the notification from me to that whenever I am uploading these videos. All of them are uploaded there. Let me just show you. This is the YouTube channel in my with my name Nilaksh Chanapati, and these are the videos latest. You can see the week 8 is already uploaded and all of the week's things, and there is a playlist where you can find that what are the things already we have. And this is the home, of course. And sometimes you can get also the community post, because I used to post it here, because then I can contact with any one of you, every one of you, whoever is subscribed my channel. So it will be good to keep an eye in this channel, to get any notification from me. And as well as you can see that many people actually use this YouTube channel chat section or comment section for the discussion purpose. If you have any problem, any query, any discussion, anything you want to ask, you can post a comment there in the YouTube channel. That is one process through which we can be in contact. Second thing is that always ask a question portal is there through the SWAM portal of the NPTEL, where many people actually ask questions. Maybe I will show you today once. Where is this what is that? So you can see this. Let me sign in. Once it will be signed in, I will show you. This is the assignments, and there is a Q&A sessions, like this is the week 0, week 1, week 2, week 3, week 4, week 5, 6, 7, 8, 9, 10. Everything is shown to you. Everything is there. You can get the lectures, you can get the quiz, you can give us a feedback. There is a problem solving session, recording, and survey things are there. You can get the links of all of these problem solving session from this problem solving session Jan 2024 thing, where if you click, you will redirect it to a Excel sheet where there are all videos uploaded from week 1 to week 8, which are already done. Today we are taking week 9, and it will be also uploaded by tonight. So these are the things. And of course this I wanted to show you once. And the Q&A, question and answer session, or ask a question portal, which we call. Here you can see that there are many questions many people used to write, and we also used to reply. You can use this portal to contact with us and discuss with any one of us, with our team, for getting response and to understand the subject more beautifully. So this is another thing. And of course you can also, I always share my mail ID also, so you can write a mail directly to me. If you have any queries, any problem, then I will definitely answer to you. There are actually many people till now have contacted with me regarding the books, or regarding like what the soft copy of the book, or what book, the references, some paper references, or something, or these kind of things, which I always used to reply and give the book support, reference support to them, which is actually very helpful for any one of you. So these are the formalities that we usually share every time in this course, and I again today again I have shared all of these things again in very elaborative and nice manner. So okay, so this is the week 9, and now we will start our discussion formally with the problem that we are doing is in the previous class. This problem we are carrying forward carry forwarding and first three part we have solved, and last seven part, that says the seven parts I told you to do it by yourself in your home. At least give some thoughts on this, but even if you have not done, then it does not matter, because don't worry, we will solve this today. We will again start it from the very beginning, that what is the problem and how to solve this, and we have already learned this. So I will show this ABC part from the previous class, and then we will move towards the these other parts which are left. So after discussing all of this this problem, then we will move towards the spatial degree of freedom entanglement, two-photon coherence, two-photon interference in the spatial degree of freedom, which was there in the lecture lecture for this week 9. And after a brief discussion of these, to recapitulate it, I will go towards this question, to answer this question and to discuss these questions, that the quantum mechanical description of physical reality be considered complete, and we will discuss about this then we'll after these theoretical discussions and some recapitulation, as well as some thoughtful understanding, we will go towards these problems, which will be very helpful for solving your quiz and assignments. I am again and again mentioning that this will be very helpful. This problems will be very helpful for your for your like quizzes or assignments or end semester examinations. Of course, if you follow these sessions, then you will be able to score very good marks, because sometimes even you can get direct question from this problem from these problem solving sessions. So all right, so this is the week 9, and we are going to start. So before starting, maybe let us wait for a few more minutes, such that some students join, and then I will start after 5 minutes. Okay, so let us wait. Okay, so let's start this problem again. We'll discuss it from the beginning. So this was the problem. It was saying that consider the one photon Michelson interferometer shown above. The state of the photon at the source is psi equal to this, where omega represents one photon at frequency omega, and v omega is the field amplitude of a stationary random field at a frequency omega. So that the probability of detecting a photon at dA is given by this pm. For that, what we did, psi e minus e plus psi and ensemble average of that. So this was the thing through which we calculated this PA and proved part A. Then it was saying that use the representation E plus T equal to A omega e to the power minus I omega T d omega, and so that E minus T equal to this. So E minus E plus, so for that E minus T equal to this, we have formula written it like this. As for the as we know it is from its description. Then we did the substitute minus w omega dash equal to omega, and do the take the Hermitian operator and all of the stuffs, and did the calculation. We reach to this, what is told to be shown. And last but not the least, and C, it was told that since the field is stationary, we can write like this is and this, where S omega is the spectral density of the field, using the above relation, so that this is it is given. So for that, first we have calculated T plus T minus T2 psi. Then we know we have further calculated it, and substituted it for the stationary random source, and then if we do all the calculation, then we reached at the solution or the form what it is told to show. Now we will go to the next part, which is part D today. It is saying that next assume that the field is quasi monochromatic with mean frequency at omega 0 equal to omega 0, so that this you need to show what is given here, where s0 omega equal to s omega plus omega 0. All right, so let us do this. 1 minute. Okay, so the field is quasi monochromatic. That is, the frequency bandwidth delta omega of the field is much small compared to the central frequency omega 0. So let's substitute omega equal to omega dash plus omega 0. We then get E minus T minus T1 E plus T minus T2 psi E, that is equal to minus omega 0 to infinity S omega dash plus omega 0 to the power minus I omega dash plus omega 0 tau d omega dash equal to the power minus I omega 0 tau minus omega 0 to infinity S omega dash plus omega 0 to the power minus I omega dash tau d omega dash, which is equal to the power minus I omega 0 tau minus infinity to infinity is 0 omega minus omega tau d omega, where is 0 omega equal to s omega plus omega 0. Alright, so this is the proof of the part D. I hope you guys understand, because all of these things are nothing but what we are doing and what we have done in the previously also, that thing only. Now in the part E, it is saying finally derive the one photon interference law, PA equal to whatever it is given, where I equal to this and phi equal to this. So let us do this again. So for this, what we need to do, we need to use the expression derived above in the previous part, in this part. And what it is told here, it is told that derive the one photon interference law. That means there will be tau equal to so what we need to do is to do what we need to do is to check the equation. I have not given any number like this part, and we need to substitute this later part like these things in these equations. Then what we will get is a psi e minus e plus psi ensemble average of it, and we will put tau equal to 0. Then what we will get is nothing but the intensity. And once we know this, then we have the form of this A, which is PA k1 square psi, which we got from the previous day's calculation. Now we need to substitute this E minus E plus, okay, and E minus E plus we will substitute after after calculating this part, and then we will substitute the first two part, and this for this last part what we will get, we will just get a cos omega 0 tau part, which we already know that whenever interference happen, then due to one is e to the power minus I omega 0 tau plus phi, and another is e to the power plus I omega 0 tau plus phi, minus phi. So if we do the e to the power plus I omega t minus e to the power minus I omega t by 2, then what we will get is a cos. So if we do all of these calculations, then what we need to finally find out is the PA in terms of I, where I is given to you. I hope you understand what I want to mean. Let me tell you once again. Here it is told that you need to calculate the this is the part E. So you need to calculate the PA, where in terms of capital I, where I is given to you, and you know how cos omega 0 tau plus phi comes. So for that, first what we need to do is that we need to substitute this this part and this part with in terms of I. After calculating it, form this equation, and then if you substitute this later part, then what you will get is nothing but the third the 2k1 k2 that thing. So this is how that means what we need to do is nothing but we need to find out this PA in terms of I, and for that we need to calculate this E minus E plus for t minus t1, t minus t2, and t minus t1, t minus t2, both different. I mean cross correlation and intensity terms. So that's what we are doing. We will do here. I will not as I have described it very well and very well manner and in elaborative manner, and I have also done these kind of things previously, so I will not do I will just show you that how we are getting I, and then I will directly write the equation whatever we are getting after substitution. Okay. Now substituting all of these into the equation, and if I write in terms of I, then what we will get is nothing but this. The definition of gamma and all of these are known to you at by now. Those things are done several times. So, and phi is equal to argument of k star 1, k1 star k2, argument of gamma tau. One printing mistake is there, that it will be k1 square I plus k2 square I. Okay. So, I'm sorry, there is a printing mistake. It is written k1 square time, k1 square both the time. So one will be k1 square, another will be k2 square. So once you get this, you just substitute all of these terms, and after calculating into this PA, then what you will reach you will reach to this equation. I am not doing step by step manner, I have mentioned it several times, so you just try to do the steps to reach to this equation. Now in part A, if it is asking the above expression is the same as that we get in the classical treatment, discuss what are differences in the two treatments, describe the situation in which the classical treatment would be inadequate. So the answer is that in the classical treatment, the interference is always explained in terms of division of field amplitude that I have mentioned. The use of analytic signal to separate out the positive and negative frequency parts of the field is only for mathematical convenience. One actually only deals with the real field in the classical treatment. On the other hand, in the quantum treatment, the negative and positive frequency parts of the field have definite meanings in terms of creation and annihilation operators, that we know that if it is E plus, then it is it is A dagger, and if it is E minus, then it is A. That means creation and annihilation operator. Now, when it comes to explaining interference of photons at a single photon level, the classical description becomes inadequate since a single photon cannot be divided. So, while the classical description based on division of amplitude implies division of energy as well, the quantum description based on the division of wave function does not imply division of energy. Okay, so this is the answer, and this thing was discussed with you in very first class, in the first classes also. So this was the F, and now the problem G. It is saying take S omega equal to whatever it is given. Here delta omega is the standard deviation of S omega, that is the frequency width of the field. Calculate gamma tau, and so that the coherence time, that is the standard deviation of the gamma tau, is 1 by del omega. So let us do this. Gamma tau equal to minus infinity to infinity S0 omega to the power minus I omega tau d omega minus infinity to infinity S0 omega d omega. After using the Gaussian integrals deriving during the previous homeworks and class discussions, and we can show that S0 omega e to the power, this part is nothing but e to the power minus tau square delta omega square by 2. This was done previously. Please go visit and check where it is done. If not, then do it again by yourself, and this part will be 1. So finally what we will reach at tau square delta omega square by 2, and the standard deviation of the distribution is 1 by del omega. Thus the coherence time is this. Now describe both classically and quantum mechanically what happens to the interference law when tau greater than tau c. Tau c means the coherence time. When tau greater than tau c, that means the coherence time, then gamma tau tends to 0. We can see that from the previous equation. This means that the interference is no longer there. Classically, it means that the two fields reaching the detector through the two alternatives have become incoherent. That is because once the field points are separated out by more than the coherence time, there no longer remains any correlation between the electric field vibrations at the 2 points. And quantum mechanically, this means that photons arriving at the detector through the two alternatives have now become distinguishable. That is, it is indeed possible to, in principle, to find out which alternative a photon came through. Okay, so there will be basically no interference. That is the answer. Now it is told that from problem G, sorry, not GGHI. Assume the central wavelength of the source is lambda and it has a wavelength bandwidth delta lambda. Calculate the frequency bandwidth delta omega in terms of lambda and delta lambda. Calculate tau c and plot gamma tau in terms of, for lambda equal to 700 nanometer and delta lambda equal to 1 for 3 cases, 1 nanometer, 10 nanometer, 100 nanometer. Alright, so I will give you the formula. You need to plot it. Plot is your homework. And we all know omega is equal to 2 pi c by lambda. So d omega is equal to minus 2 pi c delta lambda by lambda square. So delta lambda can be 1, 10 and 100 in nanometer. So what will be delta omega corresponding to that? Please calculate that from this. And what will be the tau c? Tau c equal to 1 by delta omega. You need to calculate that also. So find these three values. Find these three values. Now as you know the formulas, you can you know the formula of gamma tau also, you know the formula of delta everything. So now just substitute and check what are the plots coming. You need to plot gamma tau versus tau. One minute. I'm sorry. Okay. So this is the thing that you need to do. This plot is the homework. And now explain why the coherence time depends on frequency bandwidth. In a continuous wave field, the electric fields at different frequencies remain completely uncorrelated. Because of the presence of multiple uncorrelated frequencies, the correlation of in temporal domain exists only over a certain range, which we call is coherence time. Okay, so it depends on the frequency bandwidth that we have seen. The tau c is directly depend on the delta omega, that is 1 by delta omega, and delta omega is the frequency bandwidth. And why so? I have mentioned. Now also, can there be a situation in which the frequency bandwidth has no effect on the coherence time on the field? Yes, like if the electric field at different frequency remain correlated, then the entire fields remain completely correlated, irrespective of the frequency bandwidth of the field. One such example is a pulsed laser field, in which all the different frequencies are phase locked. So this is the part G that I described. So this was the part. Then I will discuss a few things about this temporal about the temporal about the spatial degree of two photon interference in the spatial degree of freedom, which was given to which was described and in the detailed manner in your lecture for this week 9, but I will just give you a glimpse. That I have already mentioned that the two photon interference can be observed with the all of the degrees of freedom that we have, like temporal degree of freedom, spatial degree of freedom, polarization degree of freedom, as well as orbital angular momentum degree of freedom, or angular OM degree of freedom. So for these also, what we do, we found the two photon state produced by the parametric turn conversion in the spatial degree of freedom, and we use rho, j, omega now for a particular omega. Rho is rho and q basically, where rho is the rho is the position, rho is equal to xy, and q is the transverse momentum, which is conserved always. And we, in case of this chi2 material, we have plotted we have described the theory for temporal. Similarly, in case of here also, you need to do 1 minute. You need to write the interaction Hamiltonian first for the down conversion. Then you need to write do the mode decomposition, like you need to write the electric field plus minus in terms of the a dagger, that means the creation and annihilation operator. Then you will find the interaction Hamiltonian, and then you will need to do the Schrodinger equation evaluation. Then after doing that, you will get the solution of that, which will give you the psi tp, that is the two photon state in case of spatial degree of freedom. Now just the degree of freedom is changed, as well as some notations are changed, otherwise everything is same. And you again you can have three cases, like signal and idler emission directions are fixed, and so for that you will get one case that where you can use the Dirac delta function. So again, case 2 is for the signal idler fields are monochromatic. You can also get you can use find that for for that also you can find the two photon state for spatial degree of freedom. Okay, so after getting the two photon state, you can again do the same calculation for the two photon interference. Also, what we did in case of spatial degree of freedom, like whatever we did in case of temporal degree of freedom. And this figure is showing that partial coherent pump is coming, and it is producing two photon interference in the spatial degree of freedom. The details calculations was shown to you for was shown to you for this spatial degree of freedom thing. So right now I will go for a 5-minute break, uh, and then I will discuss about this can the quantum mechanical description of physical reality be considered complete. Okay. All right. Okay. Okay, so now let us discuss about this question, which is written, and you can see there in the slide, that can the quantum mechanical description of physical reality be considered complete? I have already started discussion on this thing previously in the previous class, but let me tell you once again that Einstein, Podolsky, Rosenpreber presented an argument to show that the quantum mechanical description of physical reality is not complete. Okay, and according to them, uh, in this paper, they started by defining a physical reality, and according to them, if without in any way disturbing a system, we can predict with certainty, with the probability, that means that with the probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Next, they observe that in a complete theory, there is an element corresponding to each element of reality. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. In quantum mechanics, in the case of two physical quantities described by non-commutating operator, the knowledge of one precludes the knowledge of the other. Then either the description of reality given by the wave function in quantum mechanics is not complete, or the two quantities cannot have simultaneous reality. Consideration of this problem of making predictions concerning a system on the basis of measurement made on another system that had previously interacted with it leads to the result that if one is false, then two is also false. Thus, one is thus led to conclude that the description of reality as given as a function is not complete. That's what they concluded. And this theorem, this thing was proven to you in the in the lectures. Maybe I will go to the lecture and tell you about that uh, how it was solved. So you can see the lecture notes are present here, where it is told about the projective measurement and quantum measurement, and how that completion relation represented is like, how is this happening. Okay, and it was described in very uh, detailed manner. Like, from here you can see that it is written all of these things whatever I have just mentioned from the EPR paper. The EPR paper is given over here. Now, can the quantum it is saying, suppose a one particle system is in an eigenstate. Let me uh, let me go to the full screen mode. I just want to recapitulate this and make you understand what is the entanglement, and why is this so question is so relevant, why it was so relevant at the time, and how this was solved with the presence of quantum entanglement, and how it is resolved. So for that, suppose a one particle system is in the eigenstate AI of some measurement and AI and of some measurement operator A corresponding a physical observable quantity. Now if you measure that, that means A dagger AI, then we will get AI. So for the momentum eigengate in the position basis, you can write this x psi p0, where psi p0 is a one particle system in one of the momentum eigengate, and this is a plane wave, and momentum operator in the position basis is p equal to I minus I bar by del x. Action in the of the momentum operator, if you do, then you will get this. Thus, for a system is one of the quantum momentum eigengate, there is an element of physical reality associated with the momentum is present there. Now what about the position? For position x, that means corresponding to that, it should be like x equal to psi p0 equal to a 1 minute. Yes. What about the position? That it means that it is not equal to a psi p0. position probability particle p x1 x2 is equal to x2 minus x1. That means we can, if we know the momentum in certain manner, then we cannot tell about its position in very certain manner. It will be within a width, that means x2 minus x1, but not a particular point. So particle is equally likely to have any position. Now let us consider a particle in a position eigengate phi x0 and wave diffracting from a point. Then what we have in the position eigengate in the position basis is like this, and action in the position operator is this. Then what about the momentum? Momentum is not fixed. That means if we can measure the position, then we cannot measure the momentum. Then what is the probability that particle is found to have a momentum values between p1 and p2? That is nothing but this p2 minus p1, that is a momentum with not the particular momentum. So particle is equally likely to have any momentum. So this is why we know that delta x delta p greater than or equal to h bar by 2, that is the Heisenberg uncertainty relation, and it is telling two non-commutating operators such as position momentum cannot be simultaneously measured with arbitrary accuracy. The measurement accuracy are it is written as dictated by the uncertainty relation. So, and this was the very first principle of quantum mechanics. Now if we have a particle, a two particle system, which means psi x1 x2 and psi p x2 psi p up x1, the for first particle it is psi p and up is for the second particle, and this is a continuous superposition of two particle state. Upon measurement, what we will get if we this is a momentum operator and correspond if we corresponding to x2, and this is a corresponding to the first particle, and this is corresponding to the second particle. So if we measure the first particle and find it be in the momentum eigengate up x1 with momentum p, and then the second particle is guaranteed to be in the momentum eigengate psi p x2 with momentum minus p. If we do the simultaneous measurement for them, then we can get both the particle with momentum p and minus p. So it was telling that there is some contradiction with the very first principle, that is the Heisenberg principle, for this two-photon state. Then therefore they have then it is shown that with this calculation, if you can see that if we measure the first particle, whatever we have got, then if we do the similar thing for the eigenfunction of the position operator with the position operator, then what we will get is if we measure the first particle and find it to be position against v x1 with position x, then the second particle is guaranteed to be at x plus x0. That means we can if we know the position of one particle, then we can know the position of another particle, and similarly for the momentum. So if your question was that we find that the second particle can either be momentum against it or be in the position against it, depending on the measurement performance. But according to the first principle of quantum mechanics, that is the Heisenberg principle, a particle cannot have simultaneous reality. And thus EPR question was, is quantum mechanics complete, or does it require additional hidden variables to explain measurement result? So this was a huge debate and long term, and it went on for a long term. So all the calculations are there for you, if you and so now we need to answer that what is the hidden variable theory and how it was removed. Okay, but this apparent contradiction what I have just shown, and from the lecture, that with the first principle of quantum mechanics, it is referred to as the EPR paradox, which conclude that the quantum description of physical reality is not complete, and that it should be supplemented by postulating an existence of hidden variable, the specification of which will predetermine the result of measuring any observable of the system. Now, EPR's inherent belief was that the predictions of quantum mechanics are correct, but only as a consequence of statistical distribution of the hidden variables. And this hidden variable interpretation of quantum mechanics was formally constructed finally by David Bohm in 1950s. Bohm believed that hidden variable series lead to precisely the same results for all physical processes as does the quantum theory, while providing a precise and continuous description of all physical processes. and for quite some time there was no conclusive way to test the validity of these two theories. And finally in 1964, Bell came up with his inequalities, an experimental violation of which ruled out the local variable interpretation of quantum mechanics. So after this, we will talk about the hidden variable interpretation of quantum mechanics in the next class, and then we will go to the Bell inequalities. Once these things will be done in the next class, then it will be even more smoother to understand and go and directly study the entanglement verification. Then we will study about the entanglement verification, which we normally do in case of our experiment. We will found the like something on concurrence. Then we'll go to the entanglement quantification for the polarization degree of freedom and connection between coherence and entanglement. Coherence and entanglement, and then finally we'll go to the quantum cryptography, some protocol BB84 or Ricard type protocol here they will discuss, and then we'll move towards the then we'll discuss some part of quantum teleportation, and by this way another 3 weeks will be ended, and we'll sum up the course in the last week. So this is the plan for upcoming next week, next three upcoming 3 weeks, last 3 weeks. So I hope you have understood, you have enough background now about the generation of entanglement, as well as how the understanding of how the EPR paradox came into the role, and how we can now violate it with the hidden variable theorem. And now we'll do the detailed description of hidden variable theorem and entanglement verification, all of this from the week 10 11 10 week 10, and the lectures are already uploaded for week 10, and we will discuss in the next Saturday. But before that, today this is the theoretical part that I wanted to discuss. Now we will again move to the problem solving part, where we will solve again some more questions, of course, such that it helps you in case of your uh, quiz assignments and end semester exam. Okay, so let us wait for 2-3 minutes, and then we will start this. Let us solve this problem, which is written as problem 2. This is saying that consider the interferometer shown in this figure, where phi is the phase introduced in one of the paths of the interferometer. Write down the output field operators C and D in terms of input field operators A and B, which is the first question, and then we will read the second and third question. So this is the question. So now let us I hope you have read this question. Now we will write this in terms of in terms of A and B, which is very easy for the first question. C cap is equal to e to the power I phi by root 2, because there is 50-50 dividation of the field. As it is 50-50 means splitter, so we can write the C as minus IA minus B and e to the power I phi due to the phase in due to phase introduction, and this is due to the phase introduction. Write down the this is in the path C, and for the D there will be no phase and everything will be same, apart from now it will be minus A minus IB cap. Okay, because why? Because this is due to the, in case of C, B is the transmission and A is the reflection, and in case of D, A is the transmission, B is the reflection. I introduce due to reflection. Okay, so let me this is like this. And now part B is saying, assuming theta to be very close to 0, theta is shown here, write down the field operator F at the location of the detector in terms of the input field operators A and B. F is nothing but C plus D, which is equal to the power I phi by root 2 minus I A cap minus B cap plus minus A cap minus I B cap. So this is the F operator at field operator F at the location of the detector in terms of the input field A and B, where theta is small. And now part C is telling, suppose that the input state to this interferometer is a 1 photon state given by psi equal to 1A 0B. Calculate the 1 photon absorption probability at the detector location in terms of phi. So this is the part C. The 1 photon probability amplitude is equal to psi F dagger F psi, that is one A 0B F dagger means f dagger means e to the power minus I phi by root 2 I a cap minus b cap plus 1 by root 2 minus a cap plus I b cap into f e to the power I phi root 2 minus I a cap minus b cap plus 1 by root 2 minus a cap minus I b cap 1a 0 b. If you calculate all of this, do the steps by yourself, then you will find it as 1 minus sine phi. Final answer. Okay. Now next problem, problem 3. We'll do the problem 3. Before that, again we'll take some I will give you 2 to 3 minutes. Just read it once and then try to solve and understand what it is saying here, because now by this time we have done this kind of things so many times, and I just did this problem, this previous problem. Right now it will be just like similar kind of thing, with the input state is different and the path is different. So please try to do it by yourself. Meanwhile I will give you 3 minutes, 3 to 4 minutes to do this problem, and then I will solve this problem. So your time starts now. You can try it. Okay, so now let us read this problem and solve this. So it is saying consider a two-photon state produced by parametric down conversion in terms of the mode levels A and B. The two-photon state is given by psi equal to 1A 1B. Assume that the beam splitter is arranged such that the Hong-Mandel effect takes place at the beam splitter and that phi is the phase introduction in the one of the arm of the interferometer. Write down the state of the two photons right after the beam splitter in terms of mode level C and D. So it is a two photon state and it is passing through a beam splitter. So either for the like since the Hong-Mandel effect causes both the photons to go one way or other, so we can write the two photon state like, let me write that whereas so this is the answer that this can be written in terms of like this for the Hong-Mandel case. Hong-Mandel effect. Now B is saying assuming theta to be very close to near 0, write down the field operator F at the location of the detector in terms of the field operator C and D. Okay, very easy again. The field operator is F is F dagger equal to C cap e to the power I phi plus D. Why? This is due to the phase introduced there in this path, C path, and D there is nothing, so there will be no extra phase in there. So this is a thing for the part B. And for part C it is saying assuming theta to be very close to 0, calculate the two photon absorption probability at the detector location in terms of phi. Two photon absorption probability. Which is equal to psi F dagger F psi. Using the form of the operator F and the state psi, which is given above, like psi is this one. Let me maybe write for you once again. This is the psi. And this is the F. Where using the form of the operator F and psi in this type, we will now calculate this. Okay, so let me write 2. If you do so, then you will get 4 into 1 plus cos 2 phi. Okay, this is the answer. Do the calculations, in between calculations by yourself. I have already calculated. So the problems are very easy actually. You need to just think and do it. So this is the problem 3. Now this is the problem 4. Again I will give you 5 minutes. It will be like just the same what we are doing currently, but now we need to do the find out the coincidence count rate also. So please read this problem, and then we will please read this problem, then we will come back again and solve this problem. Let us now solve this problem, which is shown over here, problem 4. We'll now read this problem and solve it. Actually, for solving this thing, I will give you some hint, then you try it by yourself in your home, then we will solve. I need to show it with the figures. I will show the figures to make it more clear on the next day that how to solve it. And before that, I will just do it for you, such that whoever can understand. I hope most of you can understand, and so that's why I will do it, and you just try to understand how this has happened, how this is happening. And then with the illustrating with the figures, I will again tell you and convey you that how to solve it in the next class. So the question, it is saying that consider the Hongo-Mandel experiment. Assuming theta equal to 0 and kt equal to 0, find the coincidence count rate of the two detectors. The formula is already known to you from your theory part, theory in lecture notes. This is the formula for finding the coincidence count rate, RSI, from the two detectors in this kind of setup. The expression for the one photon detection probability Rx at detector Dx in a two photon interference experiment will be nothing but, for doing the one photon detection probability at detector Dx in a two photon experiment is nothing but Rxyi, where I equal to 1 to n. This kind of thing we need to do. But before doing this thing, what we need to do is, for this setup, what will be the delta L dash and delta phi that you need to find out. These are the hints that I am giving that you need to do. Then I will show the figure to you, and then we'll do it on the next class. At least for the first setup, I can give it is very easy. For the first setup, I am writing what are the delta L dash, delta L delta phi. I hope you will be able to understand that how I am writing this. If not, then please ask me, and I will show this again on the next class. For the second setup, try to find out this. So once you know this, then what you need to, once you know this delta L dash and delta phi, once you know this delta L dash delta phi, then you can find out the RSI, that is a coincidence, very easily. Okay. Now here please consider R1 equal to R2, that means 50-50 bit splitter and all of those. So if you write, then it will be R1 plus R2 plus, if I make it R1 equal to R2, then it is R only, R 2R into 1 minus cos that is 0, that is 4x into y delta phi equal to k. So ultimately it will become just 1 cos 0 cos pi equal to minus 1, that means cos pi, and that is gamma dash 4x. So we'll get 2r 1 minus gamma dash 4x for the first setup. For calculating the individual now it is saying in the find the one photon count rate in the detector ds and di. For that you need to do you need to find out you need to calculate the count rate that for the individual detector. We need to use the formula for one photon detection probability. Okay, and how to calculate that thing, that maybe I will not tell you these things. I will make a note, proper note of this, and then I will say that how to do these calculations. And I will make you to make it more lively and nice. I will make some figures and show you with the slides to solve this problem. This problem is actually very important and very nice problem. We'll discuss with figures. That will be very helpful for you, as well as I will be able to make you more I will be able to convey you in better way. So let me not do this. I have already given you some hint that how to do is delta L, delta S, delta phi, find those things. For RSI I have already calculated for the first setup. Then we need to do the photon count rate detector for a particular ds and di, that will show in the next class, as well as how I am writing delta L, delta L, delta phi. That although you know, but still for these two setups what it will be, that I will show with the figures in the next class. So next class, in that time, practice plus try by yourself. Okay, so these are the things that I wanted to convey to you today. And I will not go into much more thing. There are no time left today, so it's already 7. So formally I will close today's session. So today was week 9 of Coherence and Quantum Entanglement. Today is 23rd of March. We have discussed several problems. There are in this problem 1 we have 10 problems where there are several things, several conditions. You have learned how to find out the coherence time, what is the relation with the frequency bandwidth of it, and several problems, handling several problems you have learned. And then we discussed about the two photon interference in spatial degree of freedom. Then we answered and tried to discuss and understand that can the quantum mechanical description of physical reality be considered complete, what was the EPR paradox, and how the concept of hidden variable theory came into the scenario, those things. Then we came for more problems. We solved another 3 problems in this problem 2, and another 3 problems in this problem 3. I showed you that how to write the field operators in terms of the for this kind of setups. And then we were discussing about this fundamental two photon interference setup and how to do write the RSI coincidence rate and all those things, where I have given some hint, some things I have done. I hope you will try it by yourself, and then we will discuss with lots of figures and all of those to understand it in very nice manner. So this was all for today's discussion. I hope everybody has understand whatever I wanted to convey to you. And if you have any question, please write to me. email id of mine is already given there. YouTube channel, you can find this video there. It is already shared with you through SAM portal, through by NPTEL through SAM portal. And this is the YouTube channel link in this chat box. This is the drive folder link. All right, so I hope see you again in the next week, week 10, and goodbye.